Hello everybody, welcome back to the Math Fun Room. So in this video we're going to talk about Newton's method, sometimes called Newton-Raphson method. And basically the idea behind Newton's method is it's going to help us solve equations that we wouldn't normally be able to solve analytically, right, by hand. We're going to take numerical approximations. We're going to use what we call an iterative process. We'll go into those details in a second. But, in our past we've solved linear equations, we've solved exponential equations, logarithmic equations, quadratic equations. And normally in an algebra class when we solve those types of equations, the equations are set up in a way that we can solve them with analytic methods, right? Pencil paper work. The equations we're going to look at in this section obviously will be equations where we can't do that. Now, just as a reminder, right, let's say we have the equation that we have here to begin with, x squared plus 6 equals 5x. Now, if I was solving an equation like this, let's say in an algebra class, what we always do is we get 0 on one side. And then in regards to quadratics, we would factor if we could, or we might even use the quadratic formula, right? Opposite of b plus or minus square root of b squared minus 4ac all over 2a. Now the beauty of the quadratic formula is that works for every single quadratic function. That's a really beautiful, powerful result that we have there. So if the equation doesn't factor, we always find the roots of the equation, the zeros of the equation, by using the quadratic formula. Now in this example, I get something that can factor, but that's not always the case, right? So we see x will equal 3 or x will equal 2. Now if we look at this example over here, if I bring everything to one side, set it equal to 0, this example I can't factor. So I'm kind of stuck at this point. And there's no magical formula, like a quadratic formula, that helps me solve this equation. So I can't do this analytically. And same thing with this equation over here. Where does cosine x equal x? If I have cosine x minus x equals 0, there's definitely no factoring I can use there. And even if I dip into identities, I'm not going to be able to solve that either. So the conversation in this section is, well, how could we find some fairly accurate solutions to equations where we don't have analytical methods? All right, now this conversation again is in a chapter where we're talking about applications of derivatives. So this is actually really cool, this Newton's method. And I want to bring up a visualization, a graph, just to see what we're doing. The visualization helps us, kind of see what this process is all about. So if you just Google search like Newton's method Desmos, you'll find this graph, right? This built-in I don't know if you call this an applet, right, because it's all built into Desmos, but it's a cool exploratory tool. There we go. There's what we're going to call this, an exploratory tool. Now, normally when you open this graph, everything is turned off, so I'm going to turn that folder off. And if I just hit the arrow and open up what's under this folder, I can actually type in any function that I want. Now I believe this is the default equation. I might have changed it slightly. And then, here is it finding the derivative. So the people who wrote this said we need the derivative of the function, because what we're going to do is find the tangent line to this function. Let me go ahead and turn this on, and then I'm going to close this folder because I don't really need it anymore. So here's the idea behind Newton's method, right? If I am solving an equation such as x cubed minus 2x minus 5 equals 0, what I'm looking at is thinking of this as a function, f of x, and I'm finding where that is equal to 0. So I'm finding its x-intercepts, right? So when I look at the equation that we have here, we're finding the x-intercepts, right? These are the roots of the equation. Now the idea is what we need initially is like a first guess, right? So we would guess close by. Like I might pick -2, and that will eventually lead me to that x-intercept. Now for the purposes of this illustration, I'm going to pick -4 just so we can see multiple steps here. Now here's what the Newton's method will do. So with my guess, it's going to take that x value and it's going to come up to the function that we're finding the root of, and it's going to take the the derivative, right, and find the equation of the tangent line. So if I do that this first iteration, we can see that we're illustrating. Here's the x that I picked. I come up to the function, and let me zoom out a little bit, right? Here's my tangent line to that function. Now, here's how we're going to use that tangent line. We're going to look at the tangent line's x-intercept. And we're going to point out to ourselves, check it out, this x-intercept is pretty close to this x-intercept. Now, is it close enough? In this case, it's pretty far away. This looks like it's about negative 1.38-ish, and we're pretty far away. We're a whole unit away. So what we would do then is we would repeat this process. So I'm going to take this x value, come up to the function, and I'm going to say there's a tangent line here. And if I draw that tangent line, it's going to have an x-intercept that's even closer to the root of my original equation. So let me do my second iteration, and we will see that happen. So here's the tangent line here, and its x-intercept is even closer to the 0 of my function. Let me turn this first one off. And we're going to continue to repeat that process, right? Here was the tangent line, and this x-intercept is even closer. So now we're going to use this x-intercept to come up and find the next tangent line, and the x-intercept of that tangent will get me even closer. So let's do the third iteration here. So there's me going up, finding the tangent, and then that tangent line has an x-intercept that's even closer. And I'm going to zoom in here. We can see we are pretty close to that actual 0 of the function. Let me turn this one off and leave that one on. And this is the concept behind Newton's method. I'm going to continue doing this process. Let me zoom in a little more. So here's my next tangent line. Here's its x-intercept. I'm going to use that to create my next tangent line. So here would be that tangent line in blue. Now let me turn the green one off, and we can see that the x-intercept of this blue one is almost indistinguishable. It's really, really, really close. And just to visualize this further, I'm going to keep zooming in and zooming in and zooming in. Oops. Keep zooming in, right? And we can see that we're really close. And that's probably some pretty small error, if you will. We call that tolerance, right? That's probably tolerance that's really tiny. And we're probably acceptable. That's probably acceptable to us. Usually a prescribed tolerance or error that we're willing to accept. But I could continue going if I wanted. I could take the 0 of this tangent line, use it to come up to the function, and create the next tangent line. So let's do that. There's the next one. Let me turn the prior one off. Now again, the tangent line and the function are almost indistinguishable. And keep in mind, you know, when I have a curve, as I zoom in closer and closer and closer, the curve looks almost flat. And so after 4 tangent lines here, we have found an x-intercept. We have zoomed in so far that the x-intercept of that tangent line is smack on top of the other 0. All right, now maybe it's not exactly, but it's really, really, really close. I'm going to keep zooming and see how far away. See if we can start to see a gap. Oh man, look how close we had to get just to get a gap, right? So after 4 what we call iterations of this process, we are super close to that 0. And this is the idea behind what we call Newton's method. Now, there's another really cool applet that I found, and it is at interactivemath.com, right? intmath.com. Now, Desmos actually allows me to type in any equation that I want and look at the iterations. This applet doesn't. It's got some built-in functions, and it's just meant to be exploratory. And we can see that in this exploration, we're looking at really the same thing that we saw in Desmos. So here was their first guess, and they came up, right? We can see here's their first guess, x sub 0 is how most books write their first guess. This is my initial guess, x sub 0. So they come up, they find the equation of the tangent line. Here's the tangent line. They shoot the tangent line down, and its x-intercept generates the value for the next tangent line. And that tangent line has an x-intercept, and it comes up, and generates a tangent line, and so on and so forth. So we can see what this process has done is found the first tangents 0, the second tangents 0, and so on and so forth. And by looking at, let's see, look at these decimal values. When we get to here, we stop getting error out to the whatever 12th decimal place that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 if I counted correctly. So just after, let's see, 1 tangent, 2, 3, 4, 5, after 6 tangents we have accuracy out to the 14th decimal place. That's pretty amazing how accurate we can get to the x-intercept, to the 0 of the equation. And again, what we're solving is an equation that we don't have analytical methods for. We're going to use this process, an iterative process, where we find one tangent line, the next tangent line, the next tangent line, and all of those x-intercepts move closer and closer to the 0 of the actual function. All right, now here's what we're going to do here in just a second. I just want to point out to you that this is an iterative process, right? We move from tangent to the next tangent to the next tangent, and this is relatively simple to program in software, using software. And that's what we want to do. We want to develop how would I, do this in an iterative manner. What I don't really want to do is find each tangent and then find the next tangent. There's a much more efficient way in which we can do this, and we're going to develop that in just a moment here. Now, what I want to point out to you is that graphing technology, such as a TI calculator or others, actually uses Newton's method, or a slight variation of Newton's method, to find x-intercepts. So for example, if I was using TI calculator, let's say I graphed x squared minus 1, and I hit enter, and go to the graph, and let me do a zoom decimal, zoom into the graph a little. So let's say we're trying to find this x-intercept. So for a TI, to find a 0, what I would do is do second trace, and I would go to the calc menu, and I would find a 0. And it asks me for 3 things. It says, what's a left bound? So I'm going to move to the left bound. So here's the x-intercept. I'm going to move a little bit to the left, right? So my x-axis is my x value that I'm quote-unquote guessing is a little to the left, and I'm going to hit enter. And what it wants me to do is give it another guess. So I'm going to move to the right, It wants a right bound. So here's my x-intercept. I'm going to move to the right of that x-intercept, hit enter. And then it wants a guess. It actually doesn't matter where I put my guess. I could just hit enter one more time here. But what it really wants me to do is to try to get as close as possible and guess. Runs a little program in the background, and it finds the 0, finds the x-intercept of that function. So the program that it's running in the background basically is Newton's method, slight variation of that. But it is Newton's method, and it's using tangent lines to hone in, to move in closer and closer to the x-intercept. So let's talk about what would that iterative process look like to continue to move closer to the x-intercept in a more efficient manner. So, and able to develop that iterative process, let's take a look at, let's derive this process. And I want to look visually, We've been focusing visually on our explorations that we've been doing. And I'm going to try to exaggerate the shape of this graph here so we can kind of see what we're talking about. So here's some function, f of x, that we're graphing. And we're trying to find this 0. So let's say we have some initial guess. Now, as I mentioned to you, I think I mentioned to you, all software, almost all textbooks use x sub 0 to represent initial. And what Stewart does is uses x1 here. He's saying your first guess is x1. So I'm going to stick with his notation here, just so we don't get confused about what we see in the book. So with his first guess, just like we saw, we would come up and we would find the point on that graph. If the guess is x1, then we have f at x1, and let me use f here since we're talking about the function f of x, So here's my point on the graph from my first guess, and then we're going to find the equation of that tangent. So I'm going to do my best to draw a tangent here, and we're going to come down here, and we're going to find this x-intercept for that first tangent. So let me switch to green. We'll call that the next guess, the second guess. And then we would repeat that process. We would say come up, find the next point. We would create its tangent. Let me switch to gray. Right? If I find its tangent, here's my next intercept. Call that, x3. So on and so forth. All right. So let's come back to this first one. Let's talk about finding the equation of that tangent line. Keep in mind an equation of any line, the way we typically write it, is y minus y1 equals n times x minus x1. Now the x1, y1 in this formula, if you will, is the point that the line passes through. And ironically, we have written x1, f at x1 in this scenario. Now also, for this specific line, this one in red, right, we have the slope being, say, f prime at x1, right? So the slope of any line is the derivative of the function. So if my function's f of x, the slope of this tangent line is its derivative at the point x1. So the equation of this first tangent line in red has this slope, and we have the point x1, y1 that's on our graph. I keep writing y, right? We're symbolizing the y value as f at x1. I'm going to stick with that notation. So the equation of my line then is y minus my y value equals my slope times x minus my x value. All right, now so if I go ahead and solve for y, let's say here is the equation of my line if I write it as like mx plus b form. Plus f at x1, right? So just adding this y value to the other side, and we get this form of the equation. So this is the equation of my first tangent line that we have. Now remember, what we're looking for on this red tangent line that we have here is this x-intercept, and that's going to generate my next guess. So what is this x-intercept x2? Now I used green here. So we're looking for the intercept. Now remember, on this first line, this x-intercept occurs where y is equal to 0. So I'm going to come over here and set y equal to 0. And this would be the x-intercept, right? This x value would solve. I'm going to call that x2. So let me switch back to red. So we have f prime at x1, and then here is that next intercept. So I need to solve this equation for x2. That is my next intercept. So I'm going to go ahead and do a little bit of algebra and solve for x2 there. So I'm going to distribute the f prime. So I'll have f prime at x1 times x2, and then minus f prime at x1 times x1, and then plus f at x1. So we're solving for x2 here. I'm going to subtract this term to the other side. So I'm going to have, well, it's already being subtracted. I'm going to add it to the other side. So let me add f prime x1 times x1. And then this needs to be brought over too. I'm going to subtract it over. And then we have f prime at x1 times the x2 that we're looking for. So I solve for x2 by dividing f prime at x1 to the other side. So I'm going to have x2 equals, and let me switch back to red. That's f prime, right? So I'm going to have f prime x1 divided by f prime. That's going to give me just x1. And then I'm going to have f at x1 over f prime at x1. So this would be the x-intercept of that next tangent line. Now if I repeat this process, I'm actually going to get the same form, if you will. So notice that the second guess is all in terms of the first guess. So what we're going to see here, if we were to repeat this process, we're going to see that the third guess would be in terms of the second guess. And I don't want to take the time to repeat that process, but it wouldn't be difficult to do that. Feel free to pause the video, find the equation of that second tangent line, find its x-intercept, x3, and you're going to notice x3 has this form. So this is what we call an iterative process. Right? The quote-unquote next zero, the next guess of the zero of our function. Let me use purple, right? So the fourth zero, I'm just going to rewrite this way. The fourth zero is going to be in terms of the third zero, x3 minus f at x3 divided by f prime at x3. And here's an iterative process. So again, the next x-intercept is in terms of the prior one. So the way we typically write this formula for Newton's method is we say, well, the next guess, the n plus first guess, is in terms of the prior x-intercept. Oops, that's f at xn divided by f prime at xn. Now again, remember, this iterative process, if I scroll back up to my graph, this iterative process is moving closer and closer to the zero of the actual function. Right? So here was my first guess, x1. We found that x-intercept. Here was my next guess, s2. Found that x-intercept, x3. We would continue x4, continue x5, and we're getting closer and closer, right, to the actual zero of the function. Now remember, we're putting this in the context of solving an equation. So if I'm solving this equation, this is my f of x here, and I'm getting closer and closer and closer to its x-intercept by using each of these steps, each of these iterations, to eventually have some very small tolerance, some very small error. Now, as we saw in those couple examples when I was using Desmos and I was zooming in, that one example that I used in Desmos, I mean, it only took like 4 iterations to get really close to the zero. Depending on the shape of the function, right, its concavity, how quickly it increases or decreases, might take a couple more steps. In that one simulation that we had, we saw that it took us what, 7 iterations until we had, out to 14 decimal places, no accuracy at all. So, how many times do I need to do that? Well, normally like 10 is by far the most that you need to do. And with computer software, it is really easy to program this iterative process. Plugging in your first guess, then we are good to go. It moves pretty quick. All right, so let's see this iterative process in action with some actual equations. So the equation that we were looking at was what? It was x cubed minus 2x minus 5 equal to 0. Now if we look at our formula, what we need in our formula is the function's equation, which we have here. We need the derivative of that function, which we can easily calculate. And then we need our first guess, x1. Right? So with our first guess, x1, we find x2. So we're going to just note to ourselves for this particular example, f of x is x cubed minus 2x minus 5. F prime is 3x squared minus 2. And let's suppose that we want to make an initial guess that's kind of close to the x-intercept. Now, even though we haven't graphed this, we don't know the x-intercept. For this example, go with me, and we'll come back and talk about how we knew to make this guess. Let's say we pick x1 equals 2. So in my formula, right, I have my first guess, x1. My second guess, x2. Let me switch to, I'll switch to purple. That's a pretty looking color. I like that. Right, so x2 is going to be x1 minus f at x1 divided by f prime at x1. So in regards to this equation, we have x1 being 2. And then we have f at 2, so we would have 2 cubed minus 2 times 2 minus 5, and then we would divide by, I'm plugging 2 into my derivative now, that's my denominator, so I'm going to have 3 times 2 squared minus 2. Now, if we crunch all of this out, we get a value of 2.1. So I'm going to continue this process, and I'm going to find my third guess to my intercept of my function, my solution. So x3 is going to be x2 minus f at x1 over f prime at x1. Excuse me, why am I writing x1 there? x3 is x2 minus f at x2 divided by f prime at x2. Everything is in terms of the prior value. So our x2 over here is 2.1. So we got 2.1, and then we got minus. So we're going to have f at 2.1. So we're going to have 2.1 cubed minus 2 times 2.1 minus 5 over 3 times, what's happening with my numbers here? 3 times 2.1 squared minus 2. Plugging that into a calculator, we get approximately 2.0946. All right, now I don't want to be too lazy. I wanted to give a little more decimal accuracy, so I took out a calculator, and this would actually be 2.0945681211. So if I continue this process, write x4. So x4 is going to be in terms of x3. So I'm going to have x4 equals, I'm going to have x3 minus f at x3 over f prime at x3. So if I'm plugging this whole entire number in, then I'm going to be really precise. I'm going to go ahead then for the moment and get a little lazy, and let's make this 2.0946 as we had written. We have 2.0946, right, and then minus. I'm going to have f at. So I have f at, so I'm going to have 2.0946 cubed minus 2 times 2.0946 minus 5, and then I plug that value into the derivative, so I have 3 times 2.0946 squared minus 2. All right, now plugging that into a calculator, we get 2.09455147. Now we can see that out to our fourth guess, we are getting, let's see, 1, 2, 3, so let's see, we've got 09455, we've got 09456. So we got 0945, we got 0945. So already out to 4 decimal places, we're starting to have no error. We're not getting error until the 5th decimal place. Now I went ahead and typed this equation into Desmos. And here's the x cubed minus 2x minus 5. And we can see here's the actual x-intercept here. And we guessed x equals 2. So if guess x equals 2, here's my initial guess of x equals 2. And then I went ahead and created the first 10 iterations. So we can see decimal accuracy wise, here was the x4 that we got. We look at x5. Well, check that out, man. So notice that we, at this point, right, we have no more error all the way out to the end decimal place here by Desmos. So it looks like it took getting to x4 to have extremely accurate x value here. All right, so again, I want to back up here, big picture. The conversation that we're having here is an application of a derivative. So we're using a derivative to create a tangent line to move closer and closer to the zero of a function, which would be the solution to an equation. All right, so if I scroll back up to that first page, we are estimating the solution to this equation with some really good accuracy out to the 4th tangent line. And we could do the same thing for this equation, cosine x minus x. We could go through that same process. Cosine x minus x would be the f of x equation, and we're finding the roots to that equation as well. All right, now, so to carry all of this decimal accuracy that we're seeing on this applet, we really so much better to program this into, a computer. We can even program this into a TI as well if we wanted to see Newton's method specifically work through each iteration. Now, if you did a Google search for like Newton's method calculator, you'll find a couple out there that will do this process for you so that you don't have to program it, right? I mean, this is a calculus course. This is not a programming class. But one of the first types of assignments you learn in a programming course is writing Newton's method, approximating zeros. That's a pretty simple program to write. Now, some of these calculators, you'll notice you can't change the function, right? You can change it to one of pre-built functions, but you can't specifically change it on your own. There are some where you can. My favorite is Newton's method in Desmos because you can type into this equation and then see it do the iterations all the way through to some prescribed accuracy, if you will. I just want to talk to you conceptually for a moment here about the guesses that we make. Now, on this example, we guessed x equals 2, and we got to our 0 pretty quickly. What if we picked a guess? What if I picked 2.5? What would that look like? Now, if we look at the first iteration, we end up getting 2.16, 2.09, 2.09455, 2.094551485. So it takes us out to fifth to get that same value as well. Now, there's two versions of this Newton methods calculator. This was my altered version where I didn't have any of the graphs of the tangent lines. I just typed out all of the iterations numerically to see what those would be. And the original Newton methods applet that we would find on Desmos provides those graphs for you, right? So I'm going to come back here and let's type in the equation that we had. I just want to look visually again. We have x cubed minus 2x. I think I put minus 5 is what we had there. Yes. All right, now we had guessed x equals 2, and we could see the first iteration. There, that was the fifth one. We could see the first iteration, the second iteration, the third iteration. Right, and again, I would have to zoom in pretty close to see what each of those are. Right, there's my first one, and then there's my second and my third. Now, what if we didn't guess x equals 2, right? What if we guessed something pretty far off? Let's say we guessed x equals 3, right? What if we picked x equals 3? What would that look like? So if I pick x equals 3 as my guess, let me draw the first graph. We can see we're a little further away on the first graph. If we pick x equals, well, the second iteration, we're getting closer. Third iteration, fourth iteration, fifth iteration. Now this version of the applet stops at the fifth iteration and gives you that value. We can see visually here how that looks. Now what if I take another guess? What if I pick like x equals 5 and I'm pretty far away? So my first tangent looks like that. My second tangent, my third tangent, my fourth tangent. So I'm still getting to the x-intercept, but it actually takes a little longer. It might take me out to the sixth or seventh iteration to get some really minuscule error. Now I wonder what would happen, let's say if we picked x equals 1, right? So if we draw the tangent for x equals 1, we're going to actually hit from below, then we're going to go up and bounce back and forth as we come in. Let's see what that looks like. So there's my first iteration, then my second iteration, my third, my fourth, my fifth. So you can see we are eventually getting close, even though we picked x equals 1. We picked pretty far away in that case. What if I did something crazy like pick x equals, what would this be, -3? Let's pick x equals -3 and see what happens here. So there's my first tangent, right? X equals -3, comes down and shoots up to the graph. There's my next tangent. there's my next tangent, my next tangent, my next tangent, and we end up getting there. We end up getting pretty close. Now there are situations where if we have a guess, or there are situations where we can make a guess where we actually move away from the zero. We don't even end up finding the zero. Now in this particular case, if we look at, let's say, the minimum value is 0.816. So let's make that our guess. So if I do 0.816 and I find the first tangent, it's horizontal, right? And then my second iteration is nowhere, right? Because the first iteration doesn't have an x-intercept. Remember, my tangent line has to have an x-intercept, so then I could again go find the tangent there. So if my guess is at a maximum, then Newton's method will actually fail. Now, even if I don't pick right at the minimum value, let's say I move slightly off and I look at 0.8, the slope of the tangent is pretty close to 0, and that's going to take the x-intercept way out here. Now there's some situations where we'll never find the x-intercept by having a slope close to 0. There's some situations where we might eventually end up finding, and let's see in this case what ends up happening here. Fourth iteration, fifth iteration. Oh, look at that. So I might eventually end up with a tangent that would get me there in that case. If we pull up my version where I added extra values for the iterations, let's put 0.8 and let's see what happens. So here's my first x-intercept, second, third, fourth, fifth, sixth, and we might have to go out to x equals 20, right, the 20th iteration, to maybe even get close to the 0 that we have here of 2.095. So anyway, Newton's method doesn't always work. There's some situations where it might fail, but in most cases it actually works really well. And then, just to discuss another possible scenario where Newton's method could fail could be based on the domain of the function. So here I'm graphing square root of x, and of course the x-intercept is at the origin. But if I take any guess, really, I'm picking x equals 1 is my first guess, but I could pick any guess here, and we can see what's going to happen is my first x-intercept is going to go here, and then it's going to look for the function, and there is no function here. So we can see that in this case I used the graphical example. Out at the fifth iteration it's undefined, but the reality is even the second iteration the x-intercept is undefined because there is no function value at that intercept. Alright, so that's everything I wanted to talk to you about in this discussion of Newton's method. Again, keep in mind Newton's method is an application of a derivative, and that is our conversation in a chapter of this nature. I look forward to seeing you guys in the next video.